When we look at gravity acting on an object that's moving in multiple directions, we know that the work done by gravity is the force dotted with the displacement vector. In this case, the force is the force of gravity. We know that the force of gravity is only in the negative y direction, or the negative j hat direction. When we apply this dot product, then, we can multiply the x components, multiply the y components, but the x component of gravity is 0, because gravity is only in the y direction. Then the work done by gravity is only the change in the y direction. It's only the y component of the motion, and whatever the x component of the motion is, it doesn't matter. It doesn't show up at all in the work done by gravity. This is the idea behind the inclined plane, for example, that if you have to lift an object, you can deadlift the object straight up, but you can also lift the object up at a slant, and it doesn't matter how far you go in the x direction, you're only doing the work due to gravity, and you can basically spread that work out over a much longer distance than lifting something directly. But what we see, what we can conclude as a result of this, is that change in gravitational potential depends only on the object's vertical displacement. It only matters how far up and down the object has moved. So we can focus on the upward and downward motion of the object. We can neglect completely any horizontal motion of the object when we're considering gravitational potential energy. If we look at an object that goes down a curved surface, and we look at its motion, we still only need to consider the total up and down motion, its total displacement in the y direction, regardless of the shape of the actual surface. The reason for this is that as the object moves, it will always move perpendicularly to the surface, while its displacement has different directions. The combination, the sum, basically each one of these components, only the vertical component of each displacement will actually count towards gravity, because gravity is purely in the vertical direction. Thus, when you add up the contributions of the y components in each direction, that gives you the total motion in the y direction. Meanwhile, you'll have a normal force acting on the object as well, but the normal force is always perpendicular to the motion, it's always perpendicular to the displacement, and the normal force will do no work. We have defined gravitational potential energy as U is equal to m times g times y, where y is a height, a vertical height. When we're measuring vertical height, though, we can measure it with different origins. So in the cartoon we have here, we have Amber and Carlos, and they both have used different origins to measure the height of a object. No matter where the object actually is, up or down, its height as measured by Amber will always be the height that's measured by Carlos, plus an extra 9.8 joules. That extra 9.8 joules is coming from the fact that you have a mass of 1 kilogram, and you have gravity is 9.8 meters per second, and there's a height difference between the two of 1 meter. And so the thing is, as the object moves up or down, they'll still see the same change in gravitational potential energy. And thus, that's really what we're interested in, is only the change in gravitational energy, not the value of any specific value. Any specific value of gravitational potential energy is arbitrary. But the thing is, when you look at the change in gravitational potential, you'll have a final value and an initial value. And in this case, in Amber's case, her final value of gravitational potential energy will be 9.8 joules bigger than Carlos's. her initial gravitational potential energy will also be 9.8 joules greater than Carlos's. When you subtract the two, you're subtracting out that difference, you're subtracting out that baseline, and you'd see the same overall change in gravitational potential. It's just a simplification in order to define gravitational potential as mgy. In fact, when we're doing calculations, we'll always be looking at the change in gravitational potential. We can treat a spring the same way that we treated gravity before. Initially, we talked about a block that would feel a force due to the spring. We said that with Hooke's law, the spring would have use its spring constant to create a force that is proportional to the compression or extension of that spring. And the force of that spring would be external to the block. It would change the kinetic energy of that block. What we can do instead, though, instead of treating the spring as an external force acting on the block, we can expand our definition of the system to include the block and the spring and the wall. In this case, the force of the spring becomes an interaction between the block and the wall, rather than an external force acting on it. Then, like before, we can look at the work done by a compressed spring, and we can say that if the spring is doing negative work to slow the block, for example, that energy that is taken away from the block when that work is done, that energy doesn't disappear, but rather that energy shows up as elastic potential energy. And we approximate it as U sub S for U of spring, for spring potential energy or elastic potential energy, is 1/2 K times the displacement squared. The spring always has a amount of energy based on how far it is stretched or compressed from its equilibrium position, and we can include that just like we can include the force of gravity in our gravitational potential energy calculations.